Problem statement. Suppose you're given a following historical data of a student. This student, he studied for 1 hour. His score is 5. He studied for 2 hours. His score was 30. When he studied for 3 hours, his score was 20, for 4, 40, for 5, 60. So based on this data, predict the score of the student who studied for 5.5 hours. These types of questions are answered by linear regression. This session is about linear regression. So in this case, you have 5 data points for the number of hours the student studied and their score. So let's plot them using scatter plot. So the first one, 1 comma 5, that would be this point right here. This is my 1, number of hours he studied, and the 5 is would be right here, the score he obtained. Okay, the second point would be 2 comma 30. That would be 2 hours, which is right here, and his score is 30, which is right here. So that would be this point. And same way you can plot the other one, 3 comma 20, which would be this and this and this. That would be these points right here. Now, based on the distribution of these points, it seems like there is a straight line, something like this, that best fits the data. In other words, it tries to pass through every single point, but it cannot. But it kind of like best fits the line, this data. This line is called regression line. Now, if you remember from your high school math, a regression line, or any line as a matter of fact, is described by two terms. There's a A0 and then there's a A1. In our high school, we used to call A0 as y-intercept and A1 was called slope. In machine learning, we call this term as a bias term. So A0 is your bias term and your A1 is called weight. So in regression problem, we have to find this line. In other words, you have to find this A0 and A1. Once you find A0, A1, you can determine your line. Now, if you notice, this line is not going through all the points. There are errors. So for each data point, we can calculate the error. The error is defined by the actual value of y minus the predicted value of y. The predicted value of y would be the point on the line. So another way of rewriting this expression would be EI equal to YI minus YI, where EI refers to each error. So let's calculate each one of these errors. Let's say the equation of the line is given by y equal to 4 plus 9x. I'm just picking up any line. So my hour studied is 1, actual score is 5. Based on the line, which is y, your equation of the line is 4 plus 9x, the value of y is predicted to be 13. So I plot this point over here. My 1 comma 5 is this point, actual, and my 1 comma 13 is this right here. So the difference between these two is 5 minus 13. Actual value of y is 5, and the predicted value of y is 13. So 5 minus 13 is minus 8. And I put minus 8 over here. Okay, let's do the other one. Your second data point, actually the number of hours he studied is 2 hours. His actual score was 30. And the predicted value based on the equation of the line is 22. So if I plot this, 230 would be this right here. This is my actual point. And the predicted value is 2 comma 22, which is this right here. So in this case, my error would be actual value of y, which is 30, minus the predicted value, which is 22, which is comes out to be 8. And this is how I get this plus 8 over here. Same thing you can do with this point. Calculate its, its actual score, calculate its predicted score, calculate the error, then calculate the error the fourth, and calculate the error for the fifth. Now, another name for these errors are called residuals. In literature, machine learning world, you will also find this term. Now, there are errors above the line, and then there are errors below the line. In this case, this error is below, this error is above. In this particular instance, this error is below. Well, this is exact. There is no error for this point. It's pretty good. We're going through that point. This one, there is error above. So, in other words, there will be some errors that will be positive, and some errors would be negative. Now, let's look at this example shown in the figure right here. If we calculate the total error by taking into account all the signs and we add them all together, E1 plus E2 plus E3 plus E4 plus E5, we would get the total answer to be 0. Now, this is not true. You can see visually that the error is not 0, but it is coming out to be 0. And the reason it's coming out to be 0 is because of the sign. You see, this is -8. Okay. This is your +8. So they cancel out. This is your -11. This is your 0. This is your +11. So -11 +11 cancels out. And this is 0. So answer comes out to be 0. So one solution would be if we can somehow get rid of the signs, that would give us a measure of errors. And what we can do, we can take the square of the error. That would be one solution. And we add them. This is called sum of squared errors. So this is the formula for sum of squared errors. We're just taking all the errors and you're squaring them and add them all together. Another name for sum of squared errors, sometimes denoted by SSE, is also called residual sum of squared, RSS. So for the line shown over here, my RSS or my SSE is going to be equal to E1 square plus E2 square plus E3 square, E4 square, E5 square. You add them all together and your answer will come out to be 370, which will be a finite number. Now different lines will give you different error. So let's look at this line right here, y equal to 5 plus 10x. It's a different line. Now for this line, my in this particular instance, my hour studied is 1, my actual score was y, and my predicted based on this line is 15. So you can calculate that very easily. Your in this case is 5 plus 10 times x. In this case, my x is 1, right? This is my 1. So 10 times 1, and the answer comes out to be 15. So this line is predicting my score to be 15. And my error would be the actual value of y minus the predicted value of y, which is 5 minus 15 is minus 10. Same thing you can do with the second point, 2. Score in this case, actual score is 30. Your predicted value is 25. And then you can calculate your error, which is the second error for this one. Same thing with the third point, fourth point, fifth point. Now, for this line, my SSE will come out to be, just take all the errors, square each one of them, and add them together, and the answer is 400. So for this line, this particular line, my error is 400. Now let's take a look at this another example. In this case, my line is y equal to 1 plus 10x. So we do the same thing. My hour studied is 1, my actual score is 5, my predicted score is going to be based on this equation 1 plus 10 times x. So in this case my x is 1, 10 times 1, and the answer comes out to be 11 total. So my predicted score is 11. Calculate your error. It comes out to be minus 6. Calculate for the second point is 9, third point, fourth point, and fifth point. And for this line, calculate your SSE, same logic, and your answer comes out to be 320. The goal in linear regression problem is to find this line, let's say that is given by this, such that your error, SSE, is minimum. And in order to find this line, we need to know our A0 and A1. Once you know your A0, A1, you know the equation of the line. Well, from calculus, using our tools from the calculus, we can actually find your A0 and A1 that gives you the minimum value of SSE. So this is my SSE. This is the expression for that. You differentiate this expression, solve for, differentiate with respect to A0 first, then differentiate with respect to A1. Solve these two expressions. Your answer will come out to be this right here. And in this case, this x bar, it means mean value of my x data points, and y bar right here, it means the mean value for your y data points. So now let's use this on our simple example. So first, in order to find my A1 and my A0, I need to know my summation of my xi minus x mean times yi minus y mean. So what I'm doing, I'm just calculating each term separately. So I calculate my xi minus x mean. So first I calculate my x mean, comes out to be 3. I'm just taking all the points, 1 plus 2 plus 3 plus 4 plus 5 divided by 5. That gives me my 3. Then I'm doing the same thing with my score. I'm adding all the numbers together and divide them. The result divided by 5, that'll give me 31. So I know my x mean and I know my y mean. Then I create another column. I'm just doing xi minus x mean for each one of the corresponding numbers. So 1 minus 3 is minus 2, 2 minus 3 is minus 1. So I just calculate each one of the values. Then I calculate my yi minus y mean. So it gives me all these numbers right here. And then I multiply these two numbers together. So this one multiply by this one and this one gives me this column right here. Okay, so I get all my values this way. And then I'm also finding this term. Now the reason I need this term is because the denominator. Okay, all right, I got this term, then I add them all together. So that gives me the summation of these numbers, and that's the numerator right here. So this is my numerator. Okay, all right, so numerator comes out to be 120. This is how I get 120, and your denominator is xi minus x mean whole square. Okay, summation actually. So when you add all these numbers together, the answer will come out to be 10. So my denominator is 10. So 120 divided by 10, and the answer is 12. That gives me my A1. Now, using the formula for A0, which is y mean minus A1 x mean, I know my A1, which is 12, and I know my y mean, and I also know my x mean. Substituting your values, and the answer will come out to be minus 5. So the regression line that minimizes your sum of squared error is given by y equal to a0 plus a1x. Substituting a value of a0 and a1 comes out to be y equal to minus 5 plus 12x. Now let's try to compute our minimized SSE for this regression line we just found. So let's do the for the first data point. My our study is 5, score is 5. Predicted value would be let's see, minus 5 plus 12 times 1, and the answer comes out to be 7. So my predicted value is 7. Error would be actual value of y minus predicted value of y, comes out to be minus 2. Same thing I do with the second point, third point, fourth point, fifth point. Now for this line, your sum of squared errors would be you take all the errors, you square them and add them all together, and your answer comes out to be 280. Now this 280, this is the lowest sum of squared error that you can achieve from all possible lines that you draw. You can draw any line, it doesn't matter what line you draw, but each line would give you the error that would be more than 280. It's never going to give you a line that's going to be less than 280. 280 is the minimum SSE you can achieve here. So back to our problem. So in this case, you were given these 5 data points, 1, 2, 3, 4, 5, right? And so you have to predict the score of the student who studied for 5.5 hours. Well, you know your regression line is y equal to minus 5 plus 12x. The substitute your value of x is 5.5, and the answer comes out to be 61. So this is the predicted score for this student. You can also solve this problem using NumPy and scikit-learn package available in Python. So what I'm doing, I'm porting my NumPy as NP. I'm calling my linear regression model, and this is my x value, the number of hours the student studies, 1, 2, 3, 4, 5. And this is my y value, which is your score right here. So this is my score. And then I'm calling my model linear regression. I'm training my model over here. By the way you train a model is you call this inbuilt method called fit, and you give your x and give your y, and then I'm making a prediction on the value of 5.5. So somebody who studied for 5.5 hours, I want to know what is the model predicting its value, and the answer is coming out to be 61. So a side note on this bias term a0 and weight a1. Well, the coefficient a1, it controls how much of your x should influence the value of y. In other words, how much weight should be given to x. So let's understand this through an example. In this example, my x equal to 4. And let's say my value of y comes out to be 6 plus 5x. Okay, so let's say this is an equation. So if my a1 in this case is 5, okay, let's look at this equation. In this case, my y is going to be 6 plus 0.1x. So my a1 has gone down. In this case, my a1 has gone down a little bit more, 0.001. In this case, my a1 is 0. Now, let's look at this. Let's focus on the first one. So when my equation is 6 plus 5x, and you substitute your value of x equal to 4, your answer would be 6 plus 5 times 4. 6 plus 20 is 20. So in this case, because of this 20, you got 26. Now let's look at this term right here. My a1 in this case is 0.1. So 0.1 multiplied by 4, your answer will be zero point 0.4. You see, it went from 20 to zero point 0.4. So your amount of x, which was 4, it has become smaller because of the presence of this a1, which is 0.1. Now let's look at this one. In this case, my a1 is 0.001. So when you multiply 0.001 by 4, your answer will come out to be 0.004, which is more smaller than this. You see that it has become a lot smaller now. In this case, my a1 is 0. So no matter what the value of x is, your a1 is going to just turn it into 0. So in this case, what's happening is the effect of your x is decreasing, is diminishing as a1 is decreases from 5 to 0.1 to 0.001 to 0. That's why a1 is called the weight of x1, because it controls how much of your x1 is going to influence your value of y. So there are different ways you can calculate errors in regression. One of them is mean absolute error. In this case, you take the absolute value of an error. So let's say if your error is, you want to calculate, let's say it comes out to be 9 minus 11. Okay, so in this case, you take absolute value of this. So this will come out to be plus 2. That's your mean absolute error. In this case, you square the errors. So we seen this. So in this case, let's say your error EI is equal to, let's say, 9 minus 11. Okay, 9 minus 11. So in this case, you square the errors. Okay, by squaring the errors, let me just draw this error. So by squaring the errors, it will come out to be plus 4. So this is how you get rid of the signs in this case. Then you also have a root mean squared error. Root mean squared error, basically you're taking this expression and you just square rooting this. And the reason you square root it is because in this case, your error is going to be in a different unit. So let's say you're dealing in kilometers. So your error will be in square kilometers. So you want to bring it back to the kilometer unit. So in order to do that, you square it. So this is why this is your root mean squared error. So an example for this case right here. In this case, my mean absolute error would be 5 minus 7. So this right here, 5 minus 7 absolute value plus 30 minus 19, which is right here, absolute value, plus 20 minus 31, which is right here, plus 40 minus 43, which is right here, and then 60 minus 55, which is right here. Okay, and this gives me the error for each one of them. And I just take the mean absolute value and the answer comes out with 6.2. In this case, my MSA, which is mean squared error, doing the same thing, but I'm squaring now each term. And the answer will come out to be 56. My root mean squared error would be the square root of 56, which is square root of MSE comes out to be root 56. Now, another term that you'll come across in linear regression is R square. This is called coefficient of determination. So R squared, it measures how much of the variance in Y is explained by your model. And this is the formula for your R square. This SSRS right here, it stands for residual sum of square, and this term right here stands for total sum of squares. The difference between these two is over here, I'm taking each point and I'm subtracting from the predicted value of y. In this case, I'm taking each point and I'm subtracting it with the mean of each point, and I'm squaring it, adding them all together. So let's understand this through this example. So in this case, my y mean is going to be, you take all the y values and you divide by 5, and the answer comes out to be 31. So let's calculate your residual sum of square first. So in this case, I'm just taking each point and I'm squaring each one of them. So let's do the first one. So my first predicted value was, let's see, 5 minus 7. So it was 5 minus 7. Okay. And you square it, and the answer comes out to be 4. This right here. So this one, the answer is 4. Okay, and same thing you can do with the second point, third point, fourth point, and your answer will come out to be 280. So my sum of residual sum of square is 280. Now let's calculate the total sum of squares. In this case, I'm taking each point and I'm subtracting it from the mean. So let's look at this one. In this case, my first point is, in this case, it was 5, 5, and my mean value of, for y is 31. So 5 minus 31, and you square this term, and your answer will come out to be 676. Let's look at this one. In this case, I'm just taking my second point. In this case, it was 30 minus from the mean, 31, and then you square it, and your answer will come out to be 1. Same thing with this and this and this. Okay, substituting this in your R square formula, your answer will come out to be 0.837. So this means that the model explains 83.72% of the variance in scores.